Suppose we have a square matrix A of the order n by n. If we multiply this matrix with another matrix of the same order and the product results in an identity matrix, then the other matrix is called the inverse of matrix A. Here we can say that matrix A is invertible. Therefore, we can define the inverse of a matrix. If A is a square matrix of order m, and if there exists another square matrix B of the same order m, such that A multiplied by B is equal to B multiplied by A is equal to the identity matrix I, then B is called the inverse matrix of A. We have to be careful with notation used for the inverse of a matrix. The inverse of a matrix A does not mean that it is 1 divided by matrix A. It should be noted that a rectangular matrix does not have an inverse matrix, since for products AB and BA to be defined and to be equal, it is necessary that matrices A and B should be square matrices of the same order. It should also be noted that if matrix B is the inverse of matrix A, then matrix A is also the inverse of matrix B. There exists only one inverse for a given matrix. The theorem states that if the inverse of a matrix exists, it is unique. Let A be a square matrix of the order n by n. Let X and Y be inverse matrices of A. Therefore, the product of matrices A and X is equal to the identity matrix I. Similar is the case with matrix Y. Now matrix X can be expressed as the product of X and the identity matrix of the same order. This relation can be expressed as shown. Therefore, X is equal to Y. Now, we will prove a theorem on the inverse of the product of two matrices. Let's start with the left-hand side. We know that the product of the matrices AB and AB inverse is equal to the identity matrix. Let's multiply with A inverse on both the sides. Since matrix multiplication is associative, we can arrange the left-hand side of the relation as shown. Now we can simplify as shown. Now we multiply with B inverse on both the sides. This can be simplified as shown. Therefore, the inverse of the product of matrices A and B is equal to the product of matrices B inverse and A inverse. Now, let's look at the method where we will find the inverse of a matrix with the aid of elementary operations. Let's see the idea behind finding the inverse of a matrix by elementary operations. Let's consider a matrix A. We can express this matrix as a product of a unit matrix and itself. We saw that a matrix multiplied by its inverse is equal to the identity matrix. We can relate the two relations as shown. Here, you can see that if we can transform the left-hand side into an identity matrix, then by the transformation process, we automatically obtain the inverse. The transformation is done by using either row operations or column operations. If we perform the row operation, we will represent the relation as shown. On the other hand, if we perform the column operation, we will represent the relation as shown. Now, we will find the inverse of a matrix using both row and column operations. Let X be a matrix as shown. We can express this matrix as shown. Since matrix X is represented as identity matrix multiplied by X, we will perform row operations until the matrix on the left-hand side transforms into an identity matrix. The operations are as shown. Therefore, the inverse of matrix X is as shown. Now, we will obtain the inverse of the same matrix X using column operations. When we want to perform column operations to find the inverse, we should express matrix X as X multiplied by the identity matrix. Now, we will perform column operations until the matrix on the left-hand side transforms into an identity matrix. Now, we have obtained the identity matrix on the left-hand side. The inverse of matrix X is as shown. It can be easily seen that the inverses obtained by either row or column operations are the same. Note that, while we perform row and column operations, if all the elements of a row or column are obtained as 0, then the matrix has no inverse.